the doping of epitaxial layer. Doping of epitaxial layer. Okay, this is the page 201. Okay, doping of epitaxial layer. It's just obvious that when you grow epitaxial layer, you just put the dopant gas like arsenic, phosphorus, and boron, and antimony. You can see all those things. And then it's more or less like silicon epilayer growth. The kink site, using the kink site, and then layer by layer, the silicon film is going to be formed on top of a single crystal silicon. That's what the epitaxial growth. And the steps here, 1, 2, 3, 4, 5, 6, 7, 8, is more or less like the steps that has been taken for the epitaxial layer of a silicon. Just only the difference is the dissociation reaction of the dopant gas and the incorporation of the dopant gas into the silicon site. Okay, and it takes the substitutional site. So, except the fact that the silicon is replaced with the dopant atoms, everything seems to be the same. And obviously, the dopant concentration in the epitaxial layer should be proportional to the dopant gas partial pressure. Of course, that's intuitively obvious. Okay, and this is the interesting. This is interesting. I think it's an experimental result and the computer simulation. And you see, you open the dopant gas at this time, and then for some 4 minutes or so, you open the dopant gas and then cut off after 4 minutes, dopant gas flowing. And then this is a resultant dopant concentration in the epitaxial layer. See, of course, even though the gas has been on and off like this, but the dopant concentration incorporated into the epitaxial layer should not be this right angles. You can see the slow curves and in the dopant concentration. And that is what we call the dopant concentration profile has to be deviated from the ideal curves that we expect because of two facts. One is the out diffusion of the dopant gas, and the other thing is the auto doping. Okay. Out diffusion and auto doping. Out diffusion is kind of thing that this is a substrate, and let's suppose we have this thick epitaxial layer. And the substrate, let's suppose the substrate has a dopant concentration at this amount, and then you grow the epitaxial layer, and then everybody can expect that this dopant atoms in the substrate may out diffuse to the substrate to something like this, because we do the epitaxial layer at elevated temperature like 1100 to 1200 and so forth. Okay? And if you do the epitaxial layer with a doping, then the dopant concentration has to be at some point here, and then originally maybe dopant concentration should be this, but the dopant in the epitaxial layer is going to be out diffused into the substrate as well. Okay, so the resultant curve may look like this. So there is out diffusion from the epitaxial layer to the substrate, and the out diffusion from the substrate to the epitaxial layer. Now, if we have the same type of dopants, and these two things is going to be added to end up with some part, let's see. Some part is something like this, okay? These two dopants is going to be added. Now, if it is the opposite type of the dopants, then you're going to have this dopant profile, right? If the dopant in the epitaxial layer has an opposite type to that of in the substrate. So that has been shown in here. This dotted line is net profile if N2, N1 is the dopant concentration in the substrate, N2 dopant concentration in the epitaxial layer are of opposite type. Now, if they are same type, of course, then that should be added and then end up with some dotted line, the upper dotted line here. That the profile of N1 and N2 are the same type. If you use the boundary conditions, proper boundary conditions, you end up with some equation representing the profiles for N1 and N2, and that is 11 and the equation 11 and equation 12. All right. So in this example, where the buried layer is N-type, and then the collector, the bipolar, is also N-type, so that out diffusion from the buried layer is going to be added to the dopant concentration in the base, okay, in this particular example. And people use the antimony as the buried layer because the buried layer, the out diffusion of the antimony is the slowest because of the vapor pressure and so forth, okay. So for the buried layer, people use antimony and the bipolar transistors. Now, autodoping of the epitaxial layer, I don't know why they put the name autodoping for this phenomenon, but the autodoping is the things that dopant may be added to the gas stream by evaporation from the wafer backside. Okay, if you put the wafer and then from the backside, the dopant has been uniformly doped in the wafer so that the dopant gas can be evaporated from the backside of the wafer, and then it's going to be added to the next or itself, wafer itself. So wave evaporation from wafer backside, those dopant may be added to the gas stream. Okay, gas stream means that the reactant gas in the furnace, right? And evaporation from the front side during the HCl etching during the deposition. When you have a reversible process, not like silane, if you use the chlorine-based silicon gas, the etching and the deposition is going to happen at the same time. So HCl may etch, and for that etch, the dopant gas, dopant atoms may be evaporated from the surface, and then it's going to be added. And upstream sources, the successor, other wafers, and etc., etc., etc. You have a boot and the plate, and then dopant atoms which has been sitting on those successors may be evaporated to the upstream, okay? And then it's going to be added. So basically what we are saying here is that if wafer is loaded like this, okay, we have a stagnant layer, and then evaporation from the front side, evaporation from the back side of the wafer, or evaporation from the susceptors. All those sources for the dopant is going to be added to the next wafer or to its own wafer as well. Okay, now think of two cases where you have a low pressure. If you have a low pressure, then the stagnant layer, your diffusion coefficient, let's say diffusion of the dopant gas outside the stagnant layer is more feasible than the atmospheric case, because the diffusion coefficient is proportional to the pressure, inversely proportional to the pressure. So if you use the low pressure system, then you can prevent the auto-doping, because most of the dopant atoms from these sources is going to be out of the stagnant layer. But if you use the atmospheric CVD system for the epitaxial layer, then your dopant atoms from these sources cannot escape from the stagnant layer. So it is captured, captured inside the stagnant layer, so that affect to other wafers. So if you want to prevent the auto-doping, then the first thing you have to do is reduce the stagnant layer thickness or increase the diffusion coefficient, diffusion of the dopant gas, dopant atoms, so that help escape from the stagnant layer. Experimentally, auto-doping concentration is exponentially proportional to the concentration, and that experimental determined constant is going to be used for that. So it's different from system by system. Now, what we are going to have here is that this is the profile from the out diffusion from the source here, and this is the from the backside auto-doping, and this is the front side auto-doping profile. So even if you want a profile in the epi layer, you do not want any of the dopants. You want to have a pure silicon layers in the CVD furnace. But if your substrate is doped with the dopants, then in your epi layer, dopant thickness is going to have some weird profile like this, not zero. Okay? And then that can be explained in this side. Okay? This is a complementary error function has been calculated, which is the equation, I think it's an 11. Equation 11 is this. And this is autodoping from the front side. Then this L has to be determined experimentally, okay? And this is the autodoping from the backside of the evaporation from the backside of the wafer. So this is the deviation from the ideal profile of the dopants in the epitaxial layer. Now, the small contents of the dopants may affect the electrical properties, or even in the defects in the epi layers. Epi layer is supposed to be a single crystal, but if you have this out diffusion and the backside autodoping things, prevent to have a perfect single crystal in your epi layer. It may create the stacking folds, dislocations, and everything like that. Okay, so this is not a trivial question at all. See, this is the antimony. This is antimony, and this is arsenic. You see, in the antimony, you have a very low deviation from the ideal curve, but in the arsenic case, you have a significant amount of enhancement and doping in your epi layer because antimony, arsenic has a higher vapor pressure. Let's see, where do we have that? The vapor pressure. Okay. Here we go. The arsenic has the highest vapor pressure, boron, phosphorus, and antimony has the lowest vapor pressure. Okay? So the reason why I use the antimony for the buried layer in the bipolar transistor is because the antimony has the lowest vapor pressure. Okay, defects in the epitaxial layer. Let me just finish this defects thing and close today's lecture. Okay, the epitaxial defects in the epitaxial layer. You see in epi layer it's supposed to be a single crystal, right? Like the like the texture of the substrate. Epi means is equal, right? So you have a same, equal, same, things like this. So if you have a single crystal like 1, 1, 1 like this, and then if you grow the epi layer, then it's supposed to have a same texture to this. But as you see, if you have a face-centered cubic, silicon is a diamond cubic structure, so it's a kind of a face-centered cubic. It's not a close-packed structure, but it does have a close-packed, most closely packed plane in one plane, right? And then since it is the FCC, you're going to stack A, B, C, something like this, right? One planes is going to be stacked like this. That is the FCC. Now, somehow, the dopant may work for this, or other things may work this, so that A, B, C, and then A, B, C, that is the sequence for the FCC, but somehow this C is going to place on the A, okay? And then you start out ABC again to top. Then for this, you have a AB layers. Before this, of course, CVA. That is the FCC single crystal. But somehow, if you form a defect so that this C side is replaced with the A side, this is a very close side. Okay, so it is easy to form. If you have this, then you have AB, and that is HCP. The only difference from FCC to HCP is that the staking sequence is both close-packed structure. The atomic packing factor is 73%, but only the staking sequence is different. Then HCP, you are going to have a partial dislocations to form a stacking folds, so that you have FCC structures, and then suddenly you're going to have a HCP structures in the middle, and then FCC structures again, and we call that the stacking folds, right? That is very easy to form in the epitaxial layer growth. And how to prevent that? Of course, we have to. This problem is minimized by lower growth rates, higher temperature, and using silane gas, irreversible gas, at 100 wafers. Because 100 wafers less packed planes, and it's a covalent bonding, so that you have a less chance to make that misfit. For this misfit to C side to the A side is very easy in the one-on-one structures. See, in the one-on-one plane, you're going to have this parallel pipe unit cell, and we call this A, and this side is B, and this side is C, and this side is A again, right? This C side and A side is so close that you have a very good chance to have a stacking folds if you grow the epitaxial layer along the one plane. But if you grow the epitaxial layer along the 100, then that kind of misfit is you should have less chance to have that misfits. Okay, for the polycrystal, from the polycrystal, we're going to discuss about this on the Wednesday. Okay.